For the final example problem we're going to cover in this chapter, we are investigating the scenario where somebody rolls off a bed, they are in free fall until they hit the floor 0.4 meter below, and then the head will eventually come to a stop as the floor compresses. And we're going to look at what is the acceleration of the head in the scenario where the head falls onto hardwood versus the head falls onto carpet. Now, any object that is made of atoms that is pushing against another object made of atoms will cause those objects to compress to some degree. Now, the compression might be noticeable for something like a pillow or carpet. The compression might be very tiny, like for concrete and steel. But technically speaking, concrete and steel do have some degree of compression. It's just microscopic, smaller than what we could see, but it is technically there. Why is that? Well, think of objects are made of atoms. That is a very general statement, but that pretty much applies to everything we interact with in everyday life. So let's say I have an object, here are the atoms, and we know protons are at the center of the atoms, surrounded by the electron cloud. So here's the electrons clouds that make up those atoms. We know electrons are negatively charged. They repel other electrons. And here's an object made of atoms that is going to come down and push on this object. So when this object pushes onto this object, it will come down, and when it's physically in contact with it, the electron clouds are going to repel each other. That's why you can't walk through walls, because the electrons in your body are repelled by the electrons in the wall. And if I push harder, well, that means I'm pushing down harder. These electrons are going to try to get close together because I'm pushing, but they're also negatively charged, so they're going to be repelling. And I'm going to end up with a scenario where these atoms become kind of squished together. So I might end up with some scenario where there's something like this, and I'm pushing downward over here. I'm pushing downward, but the electrons are repelling each other. So you could see that there is some degree of compression. So any object made of atoms will compress by some amount. Like I said, for pillows and carpet, it might be noticeable. For something like steel or concrete, it might be hardly noticeable at all. It might be microscopic, but strictly speaking, it is there. So we are told that a person rolls off a bed that is 0.4 meters high. So I could draw that. So here's the top of the bed, here's the floor, and the person is here, but then they roll off the bed, so they begin right here with their head. Now, we will assume that they kind of move slowly horizontally. They get to this point and they fall straight down. So we won't assume they kind of travel in an arc. We'll just assume they go here, here, and straight down. So the person will roll off the bed, gravity takes over, and they fall downward. And at this moment right here, the person is falling down, and they are barely coming into contact with the floor at this moment. Now, after they first barely come into contact with the floor, a very short time later, the floor will compress by some amount. So a very short time later, the floor compresses and their head comes to a stop. So every object has some degree of compression. They're falling downward, they're accelerating downward in free fall, but then they hit the floor compresses, and eventually their head comes to a stop. Technically, this head, your fall, and then the floor compresses, and I should have drawn the head here, but that would make the picture sloppier, so I'm just moving it over here. So the way I'm going to think about this problem is the first part of this problem will be from the moment they roll off the bed until the head first comes into contact with the floor. head first hits the floor. Then the second, so from here to here will be part one. The second part of this problem, so that'll be a second part, will be the moment the head first barely comes into contact with the floor. So head first hits floor. Until the head comes to a stop with the floor being compressed. So until the head comes to a stop. So what does this look like? Well, in one of the previous problems, the problem with the student throwing the keys to the friend on the balcony, think about how we defined initial and final. We defined initial and final to mean one thing in part A and B of that problem, but then for part C, we redefined what initial and final are because we were looking at something different. We're going to do something similar here. Part one of this problem will be initial when you first roll off the bed. Final will be when you first come into contact with the floor. Part two of this problem, initial will be when your head first comes into contact with the floor. Final will be when the floor has compressed and your head comes to a stop. So, part one of this problem, the only thing influencing your motion is gravity, so you're in free fall. Part two of this problem, well, you have gravity pulling you down, but the floor is also in contact with you. The floor is also affecting your motion. Otherwise, you would just keep falling towards the center of the earth. So for part two of this problem, you're not in free fall. So for part one of this problem, this is initial and this is final for part one. But the final moment of part one will be the initial moment of part two. So initial part one, final part one, initial part two, final part two. Okay, so let's look only at part one for the moment, and we'll look at part two later. So what can I say about part one? I'm going to first, I kind of drew a picture. I'm going to set a coordinate system. Because I'm looking at part one, this is my initial moment, this is my final moment. This I don't really need to think about at all for now. So the initial moment, the moment you just barely roll off the bed, we'll assume you're stationary. Like I said before, you just kind of nudge over and then you begin falling. So your initial velocity for part one will be 0. If you are in free fall, that means the acceleration is negative 9.8. At what velocity are you moving when you're about to hit the floor? We don't know that, so I will just write v equals question mark. And I'm going to set up a coordinate system. I choose upward to be the positive direction. I am comfortable with that. I also will choose that the floor height, when the floor is uncompressed, will be a height of 0. So this is y equals 0. If I set y equals 0 to be the height of the floor, that means here is y equals 0.4. You begin 0.4 meter above the floor, you end at the floor level. So y initial is 0.4, y final is 0. At this point, I want to know how fast the head is moving when it's about to hit the floor. So pause the video, look at the 3 equations that describe trajectory in 1D motion, and think about which equation might be useful to find the velocity when you're about to hit the floor. Okay, so what we're going to do is we are going to say v squared is equal to v initial squared plus 2a y final minus y initial. Now I'm going to plug numbers in. So I could say v final, we don't know what that is, we're solving for it. So I'll write as v squared. V initial squared is 0. 0 squared is 0, plus 2. Acceleration is negative 9.8. And y final minus y initial. When you are solving these problems, you're not allowed to add or drop a negative sign. Even if otherwise numerically your answer is correct, you can't do that. If you plug everything in the correct place, the negative signs will take care of themselves. So remember to have a negative 9.8 here. Remember that this is final, this is initial. So don't flip them around. If you accidentally find that you somehow are off by a minus sign, I would say the first thing to do is make sure you have the negative sign by the acceleration due to gravity, and make sure you plugged these in the correct order. And sometimes then that will just be what's going on. So the final height is 0, the initial height is 0.4. And if I look at how I plugged everything in, here I have a v squared. I know you square something, it has to be a positive number. Well, here I have a negative, but this term also will be negative. So negative times negative gives me a positive. I will be okay. So when I plug these numbers in, I find that v squared is equal to 7.84 after I send it through a calculator. And so if I square root both sides of this, I find v is equal to plus or minus 2.8 meter per second. So I could take a moment, I could think about this result we have. I got two answers for the velocity. Mathematically, both of these answers are acceptable. But now I'm going to take a step back and think, what are these answers telling me? How do they relate to the physics of what's going on? Well, positive velocity would imply upward motion, negative velocity implies downward motion. So we know the head is falling downward, so I know that I want to keep the negative velocity. The head is not moving upward when it is in contact with the floor. So I'm going to just throw away that positive solution and find that the velocity of the head when it's about to hit the floor is negative 2.8. Okay, in this problem, we don't really need to find what the time, how long it takes to fall from the bed to the floor. If you want to do it for practice, you're welcome to do it, but I'm not going to do that in this example problem. Now let's look at the second part of the problem, the moment from when the head first comes into contact with the floor until the head comes to a full stop. So the second part of this problem is the head first contacts the floor until the head comes to a full stop. What I'm going to do also is I'm going to erase part of this because I don't really need it anymore. So I'm no longer in free fall, so I don't need that stuff anymore. I'm going to get rid of, I'll leave that go. So we know at this moment the speed or the velocity of the head is negative 2.8. And now in the second part of this problem, this is the initial and this is the final. So this is the initial now. We said the head comes to a full stop. So, well, if you're at a full stop, you're not moving. So at this moment, v final will be 0. What is the acceleration of the head from here to here? We don't know. That's what we're trying to find. So I'll just write A is... Now I'm going to, as I said before, when we work with these equations, we need to be careful about being consistent. I said ground level, in the uncompressed ground level, is a height of 0, upwards is positive. That means down here, the head will be at a height less than 0. The head will be at a negative height. That's okay. There's no reason we're not allowed to do that. It's like saying you're in a basement or something. You could have a negative height. We said uncompressed ground level is a height of 0. So I'm going to say y initial is equal to 0, and y final is equal to negative d for depth. I am being ambiguous to what the depth is. I could say d is equal to 0.01 if we hit the carpet, or d is equal to 0.002 if we hit the hardwood. So your height when you hit the ground is negative 0.01 or negative 0.02, depending if you hit the carpet or the hardwood. I just don't want to have to rewrite and do this entire problem over again. So let's ask what we know. Do we have enough information to find the acceleration of the head in the case of the carpet? Do we have enough information to find the acceleration of the head in the case of the hardwood? Do we know how long it takes the head to come to a stop? That is not explicitly given, so we don't know. So look at the three equations that describe 1D trajectory. If you look in the book, there's really 5 equations, but look at the equations we have to work with and see if we have enough information to find the acceleration of the head in this case. And if you look at it, we do. We could use v squared is equal to v initial squared plus 2a y final minus y initial. So what are we doing here? Well, I'm going to first consider the case of hitting the hardwood floor. So we'll say y final is negative 0.02. Y is negative 0.02, 2 millimeters. So I could say v squared is 0 is equal to v initial squared negative 2.8 squared plus 2a y final is negative 0.002, y initial is 0. So I get 0 is equal to negative 2.8 squared, that's 7.84, plus 2 times negative 0.002 would be minus 0.004a. And if I bring the negative 0.004a to the side, I get negative 0.004a is equal to 7.84. And I find a is equal to, when I put that number in a calculator, I get 1960. Oops, sorry, this is a positive because I'm adding it to bring it to their side. 1960. So if you hit the hardwood floor, the acceleration of the head until it comes to a complete stop is 1960 meter per second square. What happens if you hit the carpeted floor? It's the exact same thing. The only thing that changes is the depth of the compression. So if I hit the carpeted floor, I could still use the same equation. The only thing different is instead of 2 millimeters, my head will come to a stop after 1 centimeter. That's a lot better. A bigger stopping distance, that means it's lighter, it's easier to come to a stop. But the exact same method is going to apply. So I could say v squared, you come to a full stop, so that's 0 squared. Your initial velocity is still the same, so that's still going to be negative 2.8 squared plus 2a negative 0.01 minus 0. So I could again square this, multiply this, bring it to the other side. When I go through this algebra, I get 7.84 on this side, 2 times negative 0.01 is negative 0.02. Bring it to the other side. I get 0.02a, and I get the acceleration of the head when you hit the carpeted floor is 392 meters per second square. 392 meter per second square. When you hit carpet, so what is this telling us? First of all, I will say the fact that you have more stopping distance means the head accelerates a lot less, and for avoiding injury, that's a very good thing. The carpeted floor will be about only 1/5 as the acceleration as the hardwood floor. Also, I'm going to point out, notice that throughout this problem, we were consistent with the signs of everything we plugged in. We were moving downward at 2.8 meters per second. We initially had a height of 0, but then the floor compressed to a depth of 1 centimeter. I had the minus initial, -0. The final was negative 0.01. I was careful to keep the positive negative sign everywhere, and when I bring them over, I find the acceleration of the head is accelerating upward. Does that make sense? Does it make sense that the acceleration of the head is upward in this scenario? Well, let's think about that. We could show that fairly quickly by just drawing a picture. So here's the initial. We have V initial is equal to negative 2.8, and V final is equal to 0. We said that acceleration, we initially defined it as change in velocity over change in time. So I could write acceleration as final minus initial, 0 minus negative 2.8 divided by delta t. Whatever delta t is going to be, it doesn't really matter for the context of what I'm doing here. You know delta t will be a positive number because time always moves forward. This number is also going to be positive because we have minus negative. So the acceleration will be some number greater than 0. Also, if you have a negative number and then you go to 0, you increased. So that is like saying the acceleration is positive than 0. Or sorry, the acceleration is greater than 0. So this ends the second chapter of everything I am going to demonstrate as far as practice problems go. I really want to emphasize for a course like this, in my opinion, and I really do believe what I'm saying, you do not learn physics when you are in lecture, watching lecture videos in this case. You'll learn some things, but you really learn physics when you work through example problems. So my honest advice to you is work through all the example problems that you can. That is, I think, the best way to do it. If you think of a skill, like pretend you want to be a good batter in baseball or cricket if you prefer. If you want to be really good at swinging a baseball bat, you could read a book about how to properly position your shoulders, your hips, how to properly swing. That is useful, but you really hone your skills. You really master the nuances of what you're doing when you read that book of how to do it, but then you go into a batting cage, you get a friend to go out to a park, and you actually practice real life scenarios. So I'm showing some practice problems. So I noticed in the past, some people studied for physics exams by working through practice problems again that I demonstrate. That has some usefulness to it. I'm not going to knock it, but I think the best way you could practice is to go through the back of the chapter that your exam is going to be over and try to work through new problems. Try to work through problems you have not seen before. All the problems do apply the same principles that we're talking about, but just in different scenarios. And when you practice them enough, you'll realize that all these different scenarios ultimately boil down to the same principles at play And it's just developing your intuition for seeing those principles and breaking them down quickly. So if you need any help with practicing this material, I am here to help you. I really want to see you succeed. I want to see you do great things, get to where you want to go in life. And if you're willing to make the time to practice things, I will definitely make the time to help you get to where you want to go.